So I should start by thanking Subhro and Sergej for organizing this very fun workshop. I've had a lot of fun so far, and also thanks for inviting me. So we've been listening to a lot of talks about generalized symmetries and their applications to quantum many-body systems. So of course, we know symmetries have been a very kind of undeniably important structure in quantum field theory and quantum many-body systems, and they help organize many things, the representation theory of states and operators, landscape of phases. And recently, of course, there's been this development under the umbrella of generalized symmetries, which has further helped in this very important kind of question. So let me start by kind of just giving some context. If one looks at gapped phases, very broadly speaking, one can organize gapped phases in terms of the entanglement properties of their ground states. Let me say complexity. Maybe this is not a very precise definition, but and then we have short-range entangled phases, and we also have long-range entangled gap phases. These are. And we know many short-range entangled phases, such as topological insulators, SPTs, easing ferromagnets, and many, many more. And long-range entangled phases, examples of these would be toric code, the Kitaev spin liquid, fractional quantum Hall, and variants of these, for instance, string net states. And so many of these short-range entangled phases can be understood in terms of properties related to conventional symmetries, which are now called zero-form symmetries. Ground states of these look like, or they're connected to product state ground state, so you can kind of molecularize the ground state wave function. Meanwhile, if you look at a phase like toric code or the Kitaev spin liquid, the ground state looks qualitatively different. It's some kind of fluctuating soup of loop-like configuration. So they're very distinct kinds of states. And now, by now, it's already quite well known that one can organize many of these phases in terms of symmetry-breaking properties of higher form symmetries, perhaps non-invertible higher form symmetries. And so, but these phases were already known before the advent of symmetries, but symmetries still help organize order parameters, understand transitions in this landscape. Generalized symmetries also give many short-range entangled phases, which weren't appreciated, which we would not be able to appreciate if you didn't fully, we didn't study the full symmetry structure, which might include non-invertible symmetries. I'll give an example of a phase which is short-range entangled, but requires non-invertible symmetries to understand today. But then there are also some qualitatively new sorts of phases that are stabilized by generalized symmetries. For instance, you can have a phase which has one ground state, which is a product state, and another ground state which looks like the toric code. And there's some symmetry that maps between these two states. And such a phase of matter can never be stabilized by invertible symmetries, because for invertible symmetries, we have a unitary operator that maps between these two states, and no unitary operator can change the entanglement structure. So these states should look isomorphic. So there's a whole zoo of new phases. You can also find, for instance, a continuous manifold of states, or a phase of matter labeled by, this would be a gapless phase, but you could find some phase which where the ground states are labeled by points on some moduli space M, and there'll be some isolated points that look like topological orders, while the rest of the points look like trivial product states. And this looks very weird from the perspective of conventional symmetries. You never find such a phase of matter. So I want to, so kind of broad questions that one might be interested in are what kind of gapped phases can be stabilized by generalized symmetries. By some generalized symmetry S. And also, how does one realize that phase in a lattice system? Yes. Time reversal of the Hamiltonian can give you a time. Yes. Yeah, but I'm talking about pure state ground states with some symmetry, right? So you declare a Hamiltonian with some symmetries, and I see, I see. So maybe we should be more careful. I mean something that is tensor that some unity that has a certain locality. So the locality by time evolution has this Lieb-Robinson bound limit by which it grows. So if you consider very, very non-local unitary operator, you might be able to do that. But I mean unitary which has some locality properties. Thank you. So I was saying that one also is interested in constructing lattice systems that realize these different phases as well as transitions. So yeah, and also a more interesting question is transitions and gapless phases. So in today and tomorrow's lectures, I'll touch upon the first question, but totally in the context of lattice systems. So I want to describe 1D and 2D lattice systems that realize all gapped phases and also provide order parameters and so on for these phases. So the kind of models that I'll be studying are Anyon chains. And a lot of what I'll be saying is actually already been described in Frank's lectures. So this is kind of you may think of as a prequel to his lectures, but it'll be perhaps a complementary perspective. So you'll see many of the structures reappearing today. So let me define an Anyon chain model. The input data to describe this model is the following. There are 3 pieces of data. The first is some fusion category. C. The second piece of data is an object rho. In C, and rho need not be simple. And the third piece of data is a C module category M. So with these 3 pieces of data, one can first define the state space of this model. And the state space is spanned by fusion trees. Of the form, it takes I have on the vertical rungs, I put this object rho in C, and these are all oriented. And on the horizontal rungs, I put some objects in the module category. There's also something here. which are, I'm going to label it mu, and I'll describe what it is in a second. So Mj is our objects in C. Meanwhile, mu's are vectors in the morphism space. So mu j minus half is in the Helm space from and this might be a multi, this Helm space might have dimensionality more than one, in which case there's a quantum degree of freedom here. Any questions at this point? Oh, sorry, thank you. Yeah, thanks. So you take some objects in M. These objects come with a notion of how you can fuse. There's a left action on M by rho. So I should say this is a left module category. And various consistent fusion trees give you a basis for the Hilbert space. So that's the state space. And this might look a bit abstract now, but I'll show you in a couple of minutes that in some cases, this just reduces to, let's say, tensor product of qubits or some tensor decomposable Hilbert space. So this includes very conventional and well-studied examples, but it's good to formulate it like this because this is kind of general construction. Yeah. So think of, take your favorite fusion category. Let's even say it's a group, right? And I over here, I have, let's say, rho is the direct sum of 2 times each group element in the group. And I choose this such that there's a non-trivial Helm space. Now, if I choose, and let's say M is the regular module category. In this case, I can put a group element here, any group element, let's call it Gj minus 1. And here I put another group element Gj. There are 2 ways, there are 2 Gs here, such that G times Gj is Gj minus 1. Right? For any 2 group elements, so there'll be a 2-dimensional vector space here. So what I mean is in that case, there'll be a qubit here and you'll have to pick a vector in that qubit. Picking that vector gives you one configuration. It need not be, it need not grow as the power of, it's not tensor decomposable. There's some constraints. It might, oh, I see, yes, you can have a finite dimensional Hilbert space. So for example, if you take the identity here, then the number of states in this Hilbert space and number of objects in the category for some choice of module. And that's actually an important point, because what that means is that if you choose a certain kind of rho which is not large enough, that means your Hamiltonian that you'll construct, or this space of models won't have enough charges, won't have enough charged operators to drive you to different phases. So for instance, if let's say this was a group and you chose 1 here, you're automatically in the ferromagnetic ground state. You have like two vacua, and there's no way to tune into the paramagnet. So you've chosen a model which is in some sense pathological. You have a 2-dimensional vector space, doesn't scale with the system size. You want a rich enough model such that all the charged operators exist so that you can condense them and find new phases. So that's the state space. The general Hamiltonian operators. Yes. Yeah, in a sense. So you with this piece of data, you just list all possible configurations that you can find that are consistent with the fusions. Once you do that, that gives you some number of states. Those span a vector space. That's the Hilbert space of the model. They're orthogonal to each other. They're basis vectors. They define a basis. So the span of this fusion trees over the complex numbers is the state space. So Hamiltonians are so some tensor product of rows here. And I can, so any endomorphism of, actually I don't even need this. So any endomorphism of, say, row tensor rho to itself defines an operator which can be used in the Hamiltonian. And I can, so this would be, and I could choose a Hamiltonian with 3 rows that would just increase the locality of the Hamiltonian or single row. And as Frank was emphasizing yesterday, this Hamiltonian doesn't require the definition of a state space. So I haven't chosen M. I can abstractly define the Hamiltonian just using the rows. And then they'll form some algebra. And that algebra kind of constrains the spectrum of the Hamiltonian. So this Hamiltonian is agnostic of the choice of M. Once you choose M, so these Hamiltonian operators will form some algebra, and then you represent that algebra on a state space by the choice of M. But so far, it's just an algebra. So symmetry. So this model comes with a natural symmetry, which is why it's being studied in the context of these generalized symmetries. So there's a, so for the pair C and M, there is a dual fusion category. Which I'll call S because it'll be the symmetry of this model. And S abstractly is, it's sometimes called C dual M. And it's basically the category of functors in C from M to M. But so this is an abstract way of defining it, but actually it's very simple. So this S is just a set of functions or functors from M to M that satisfy the following property. So if I take for any F in S, A in C, and M in M, there's this property that so this property holds. And what this means is so if you think in terms of this model, I have some M here, and acting with A gives me A of M. And acting with F is F of A of M. This is so it just means that the symmetry and Hamiltonian action commute. Because you can first act with the symmetry operator or with the Hamiltonian operator and you get the same outcome. So this just tells us that S is the commutant algebra. And this is nice because it gives us a constructive way to build models. So you can start with S, say, choose, and I should also say that M is a right is a right S module category. Maybe this picture didn't make sense without saying this. So I just mean that you can abstractly think of it as follows. So there are the state spaces with rho and M, and some operator, which is basically defined in terms of objects in C. This is some structure in C, defines the Hamiltonian operator. And you can think of the symmetry as acting from below. And they satisfy this condition. So you can act with the symmetry first or the Hamiltonian operator first. And they commute. So we can easily construct models using this sort of structure. The symmetry action is given like this. So you take, or I'll define it in a second, more precisely. But the point is that there's this category S, and M is a right module category for S. So that already has the information of how you can fuse this. So for instance, let's look at symmetry action. So symmetry action, you start from something like this, and you can fuse using some F symbols, for instance, partially fuse it up. Sorry? Yeah, I'm just saying that given some S, I want to tell you the prescription of how to fuse it, and then you figure out the symmetry action on the basis vectors. Right. Yes. Yes. Yeah, so all of this is equivalent to Frank's talk if you squint a little bit. There are various things that are moved around. But I agree, yeah, that's right. So I'm treating M as a left module for C, which is the Hamiltonian operators, and the right module for... Okay, so you want me to change? Yes, 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 yeah. But yeah, thank you. Please point these things out as we go along. Yeah, there might be some changes. So the symmetry action I was saying is that you can use, so there's a way to fuse this partially onto this, and then you have, so this was MJ minus 1, MJ plus 1, and then you get MJ minus 1, MJ prime, MJ, because the S fusion might change this object. And then you can kind of move this. This category has information of how you can move it past a junction. So you can move this around, and after a sequence of such moving around, you end up with a state that looks like this. S, in capital S, and all the M's have been changed to M primes. And then finally, you can fuse this bubble, and it gives you a new state. So there's a constructive way to read off how the symmetry acts on the state space. Yeah. Yes, it does not. So anything constructed within this. So in a sense, you've restricted to the bond algebra of symmetric operators. That's your whole space of Hamiltonian operators. There's no way to go out of it. Actually, there is a way. Let me postpone that to the end of the... Yeah. Very good, yeah. Maybe I can just say very quickly, but it might not make a lot of sense. There are operators that you can define that have one end on this boundary, on the top, and another end on the bottom, and they kind of go into the bulk, if you wish. They go into the bulk, and when you squish these operators, if you squish this thing onto this rung, there's some action on this state space, and that is these charged operators. In fact, this bulk is the sim-TFT. And all these lines are labeled by objects in the sim-TFT, and that's why and those are the charges. The objects in the sim-TFT are precisely the charged operators. So there's a way to do this, but that'll probably be more confusing at this point. But let's say for now, we don't have order parameters. Any questions? So this M, for instance, is a left-right bimodule for C and D, for C and S. Maybe Frank has something to say, add to that. Yeah, so yeah, the CS bimodule is like this DC bimodule in Frank's language. Yeah, sorry for the confusions, but. So this is how the symmetry action is constructed. No, so it doesn't, the algebra doesn't form the category C, but the algebra, these Hamiltonians, you can think of as, let's say there's some Hamiltonian operator that looks like this. So it's a map from rho squared to rho squared, and if you choose some morphism. Yeah. So the way, so consistent operators are kind of extracted using the algebra and the category C. So you could, for instance, do something like this. Something like that. So there are these, fusion rules in C that are used to define the Hamiltonian operators. And I should also say that this Hamiltonian is Hermitian if it's invariant under flipping these arrows. So flipping arrows is like taking Hermitian conjugate, and we want such kind of string diagrams, if you wish, acting on this state space. And you can assign a coefficient to each of these. So for instance, you might have alpha, A, B, C, D, E, plus some beta, and with orientations, beta, A prime, B prime, C prime, D prime, E prime, and this is on side J. You could define a Hamiltonian like this, plus its orientation reversing. That would be a choice of Hamiltonian. Yeah, the algebra of Hamiltonian terms would be computed using these fusion diagrams. So yes, I'm not claiming that. So for instance, in this case, the Hamiltonian commutation would look something like this. Then you can move these two vertices up and down. Yeah. Yeah. Yes. Sorry. That's not. That's absolutely true. So given a C and given an M, you construct S. So there are two free choice. You can make two choices. Among C, M, and S, you fix any two of them, and that fixes the third one. I'm not saying that every M gives you the same S. They'll give you different S's. In fact, they'll give you different S's related to the generalized gauging. So those are all Morita equivalent. Yeah, this property implies that the symmetry and the Hamiltonian action commute, because the Hamiltonian action is from above. If you, yes, yes, exactly, exactly. Yeah, yeah. This is an equality. Yeah. Yes. Yeah. I think you could relax it as long as once you pull the symmetry around and you contract it, it gives that those phases cancel. I'm working with the strict version here. Yeah. So S is a fusion category. You can take composition of functors. Yeah. Any more questions? Yes. Yes. Absolutely. So if you take the product of S and S prime, you get the fusion outcome of uh, those objects in the category S. Yeah. So this model has this S symmetry, uh, an exact S symmetry. So let me see where I was going. Yeah. So one can also consider twisted sectors, symmetry twisted sectors, or corresponds to adding some charged impurities. And in this construction, it just corresponds to allowing an object in S to end on this state space. And there might be some internal degrees of freedom here. So you have to actually add some kind of a new degree of freedom. It might not be one-dimensional, this morphism space. So for instance, if the category was rep G, here you'd have the representation space, and here you'd have some representation R in rep G. And here you'd have vectors V in the representation space of R. That corresponds to adding an impurity in the spin chain. So let me now give an example. The simplest example is let me choose C to be vec G. It just corresponds to an ordinary finite group symmetry. And I also choose M to be the regular module category. So let me also write that as vec G. And for this the dual, so the symmetry is also just group-like symmetry. And I choose rho to be the direct sum of simple objects in this category. So for this choice, the state space just becomes a tensor decomposed state space of generalized spins. So let's say I'd have Gj minus 1, Gj and Gj plus 1, which are objects in M. And here we have direct sum of G. So given any Gj and Gj minus 1, there exists some a unique, of course, group element, unique G, such that G times Gj is Gj minus 1. So for any choice of Gj minus 1 and Gj, you have a one-dimensional morphism space here. You can just ignore that. That's just a number. And therefore, the Hilbert space, let's call it V, with this choice of module category, is just tensor product of group algebra defined on each horizontal rung. Which plus sign? Oh, that's just a direct sum of objects. So what that means is if you have different channels, this is not a simple object in the category. So you can for some generic non-simple object, you can ask what is the morphism space from Gj minus 1 to Gj. And what that does is just singles out the correct group element such that the group multiplication is consistent. Yes, so let's say we just have one simple object G. In that case, what you'll have is this configuration would be such that each successive group element is the previous group element multiplied by G. But then the state space would be G dimension. So look at, let's say we have Z2, right? And on each horizontal rung I put, and Z2 is, the group elements are 1 and P, let's say, and I put P everywhere. So then I'll have two states which are 1P, 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 or I'll have P1, P1, P1. So you have a G, you have two-dimensional state space here. Right. Exactly. So now you have something that grows exponentially, right? It's a spin chain. And for that, one needs this direct sum here. Actually goes back to your previous question about, what if the state space were finite? Yeah, so if you have 2G, let's look at this example again. So let's say we have 1 plus P, 2 times 1 plus P. And for any configuration, P and P prime, there are two choices here. Let's say P and 1, you could have, there are two copies of this object 1. You get a two-dimensional state space here. Maybe the Hamiltonian action also kind of is block diagonal in this morphism space, but that is not necessarily true. No. No, so what this would give you is just some state space, which would be C2 tensor product Cn, where n is this. 2 is equal to n in this case. So if you change n, you'll just, and this is at the sites being here, and these are the half integer sites in the morphism spaces. Is that okay? So this is kind of, it just recovers the usual the usual picture of G-symmetric spin chains. I can take an object G in the group. And fusing it just gives me the ordinary right action of the symmetry. So UG sends GI So now, in general, we can change the module category. And changing the module category is equivalent to gauging the spin chain. So for instance, in this context, VecG module categories are classified by tuples H, which is a conjugacy class of subgroup in G, and some 2-co-cycle beta. So what this means, if I change M from the regular module category to another module category, let me just label it by H and beta. I'll tell you what it is in a second. But if you just change this, it's equivalent to gauging H with so in condensed matter, language is gauging H after pasting an SPT. Labeled by beta. I guess in high energy it would be called discrete torsional. But so changing appropriately changing H comma beta, you recover Kennedy-Tasaki kind of duality and so on. That would be gauging Z2 times Z2 with a non-trivial 2-co-cycle. Let me. In general, if H is some subgroup, the objects become left cosets of H in G. But let me first describe the simple case of gauging the full group. So gauging this MG is vec. This has a single object. And let's look at the state space. So we haven't changed rho. But now we have a single object here. Let me just call it, it doesn't need to have a label, it's just a single object. But depending on what, for some configuration, if we, so one still gets a G-dimensional configuration space here, labeled by the object you pick in rho. One still recovers CG here. There are as many choices of this vertical rung as group elements, and for a choice corresponding to the group element G, you get that vector in this space. So this V labeled by MG is again just group algebra on the half integer sites, if you wish. And let's see the symmetry action. The symmetry action, okay, I should first say that the dual symmetry, so C dual M is rep G. So we should recover some spin chain which is rep G symmetric, so has a non-invertible symmetry. And let me describe the symmetry action. So we've got now some group elements on the half integer sites that live on the morphism spaces of this Anyon chain. And let's see how some symmetry operator labeled by a representation R in rep G acts on this. Are there any questions at this point, actually? So what we've done is we've taken like the most boring G-symmetric model. It just has a tensor product of G degrees of freedom, if you wish, on each site, and we've gauged it, found some dual model where the G degrees of freedom live on half integer sites. And then the symmetry, we're trying to recover the symmetry action. And as I said, what one can do is fuse this, this line partially. So I could take this segment, for instance, and fuse it onto some region here. And what that gives is the direct sum of vectors in the representation space of this representation R. You get some vector V, and it's dual in the dual representation space. So start taking a fusion of these should recover the identity representation. And now we can move this, we can move this past. What it gives is we get some V prime, V dual, Gj plus half. So it doesn't actually change the state space, but you pick up a phase which depends on the representation R evaluated on the group element Gj minus half. And this is in general a matrix, you pick up the V prime element of that matrix. And then one can drag this all the way around the spin chain. So I'm considering some periodic boundary conditions. So we have right now a picture that looks like this. And we drag this all the way around until we come back here. So eventually what we get is this. We get a product of J minus half taken from here all the way around the chain. V double prime, and we finally end up with some vector V double prime. This is V dual. And these states, the configuration hasn't changed. But now V dual give you a delta function. When you collapse it, you get a delta function onto V because otherwise it's zero. There's a correct dual vector. Yeah, you're actually right. So actually, I'm allowing for this kind of phase, so that it has to be more general. Yeah, I think I misspoke over here. Was this your question? Yeah, because you see, we're picking up, we're evaluating the group element on the representation as you move the. So in the end, we get some delta function. Therefore, we just we get the same state. And this is nothing but the character of the representation R, evaluating the holonomy of this configuration G, the holonomy just being this. So in general, what we find is symmetry operator labeled by R acting on some configuration space that looks like this. So some state in this Hilbert space that looks like this just picks up the character of product of. So, I mean, this procedure is very general, so one can actually construct. I just described it for group-like fusion categories and one kind of gauging, but it works very generally. Are there any questions? It acts diagonally here on this like computational basis. Yeah, you could literally just, say you had Gj plus 1. So this is the G-symmetric model, the symmetry G. One can turn on, so let me gauge all of G, for instance, again. Yeah. Yes. Yeah. Which would not generally be true if you change the fusion category or for some partial. Yes. So if you gauge a non-normal subgroup, you'll end up with a constrained Hilbert space. Yeah. So gauging, the conventional gauging is in 2 steps, right? You introduce extra degrees of freedom, add like gauge degrees of freedom on edges, and then you impose Gauss law, right? Which would be something like G, Gauss law would be something like the G action. Let's say, it would look like this, left or right G action at some site J, at some site I, and then left G action at site I plus half, and left right G action inverse at I minus half. Sum over. This is the general Gauss operator that one has its I. Now there's a way to kind of solve this Gauss constraint, if you wish. So this will give a constrained Hilbert space with degrees of freedom both on the edges and on the vertices. And then upon solving the Gauss constraint, you end up with a dual model or the gauged model with degrees of freedom only on the edges. You're picking some gauge and solving the Gauss constraint. But the nice thing about this is kind of that you don't need to do all that. You just land up directly on the gauged model. Yeah, it depends on how you want to define it, yeah. But this also works. You just project onto the singlet sector of the local symmetry operator. So the reason I define it like this is because I want my Gauss operators to commute. If I have a non-abelian group and I define Gauss operators labeled by individual group elements, they'll satisfy the group algebra on like. Yeah. Yeah. I mean, this also projects onto the same space. Yes. Yes, yeah. So if you gauge a subgroup, let me say H in H, then what will happen is one can, a configuration that looks like Gj in the projected subspace would be the same, would be connected by the action of the Gauss operator to some state that looks like HGJ for all H, right? So in the end, after solving the Gauss constraint, you'll be able to label states by cosets. And in fact, objects in the module category also labeled by are labeled by cosets, H cosets in G. So that it's really the same. Yeah. So this is so it matches up with conventional gauging. Yeah. So we can. So as I said earlier, that one can also construct fixed point Hamiltonians, so commuting projector Hamiltonians in each gapped phase. Do you have a question, Julian? So it turns out that fixed point Hamiltonians or gapped phases the set of gapped phases is there are many ways to see this, but the set of gapped phases is equivalent to the set of module categories also. There's also something that Frank was emphasizing. To see module categories or equivalently Frobenius algebras. And so given a Frobenius algebra, A and C, one can define a Hamiltonian. So firstly, A is some collection of objects in C, and along with the multiplication and co-multiplication rule. So you can use that so this Frobenius algebra is some Y algebra. It has some map M from A, tensor A to A. It also has a co-product from A to A tensor A. So using this information, which is kind of native to the Frobenius algebra, one can define a Hamiltonian, which just looks like this. And you see here we use the co-product delta, and here one uses the product M. And this acts on the spin chain. These are in fact also labeled by the same pieces of data that I said. So let me, since it's getting a bit abstract, let me try to construct the simplest case before describing the more general stuff. Yes. 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 Yeah. Yeah. So rho is some collection of objects, right? Rho is an object, possibly non-simple in C, right? Now A, basically the action of this operator projects the state space into the A inside rho. Yeah, yeah. Yes, yes. So let me give an extremely simple example, and then that should already give you intuition about what rho should be, and those sort of things. So let me illustrate this with an example. So let's say G is equal to Z2. You have just a tensor product of qubits, right? And there are two algebras. There's one where A is 1 plus the non-trivial group element P, and there's another algebra where A is just 1, and there's no 2 co-cycle here. So let's see maybe let me do A equal to 1 first. So what this does is recall that rho was 1 plus P. And here we had group elements, Gj minus 1, Gj plus 1, right? So what A equal to 1, actually we can even take a simpler Hamiltonian, which is just a projector from rho to A. So this is A in this case. And you see what it does is it projects this state space into the sub-configurations where you have 1 on this horizontal run. So that means Gj minus 1 should be equal to Gj, right? So the ground state, there are 2 ground states. Ground state 1, which is just 1, 1, 1, 1, 1, and ground state P, which is just P, 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 P. And this Hamiltonian, which is just minus J plus half, A at J plus half, just turns out to be 1 plus ZZ over 2, where Z is the Pauli-Z operator. It's just a projector on, it's just the usual ferromagnetic Hamiltonian. Now, instead, if you take 1 plus P, what that does is for any configuration, it gives you a sum of G there's a G here. So this Hamiltonian is nothing but 1 plus X over 2. There's a normalization which I wasn't very careful about, which is the paramagnet. Now, if we had a non-trivial 2 co-cycle, oh, okay, sorry, yeah. So in such a way, one can construct these commuting projector Hamiltonians in each ground, for each gap phase. And what, so just to mention, SPTs would correspond to Frobenius algebras that are labeled by a non-trivial 2 co-cycle as well. And there'll be some additional phases that will come from the product and co-product in this algebra. Yes. So Frobenius algebra is some collection of objects. It has a multiplication and a co-multiplication. And I forgot to mention, there are some Frobenius relations that it satisfies. For instance, this must be an equality if each of these is A, and you choose M and delta appropriately. You can move these rungs. You can move one past another. So this is one of the properties of a Frobenius algebra. And what you can see is that this is nothing but acting with, so let me call this kind of a structure acting on side J as my Hamiltonian operator at side J, little hj. So what this condition tells you is just that hj plus 1 is hj plus 1 hj. So kind of the fact that it's commuting projector automatically is built into this Frobenius condition. There's some choice of morphisms in C. So for instance, if you take Z2 times Z2, the fusion is according to group multiplication, right? Vec Z2 times Z2. But what this choice of beta does is if you take G1 and G2, you get G1 times G2, but the morphism picks a U1 number. And that U1 number is precisely the one given by the two-core cycle. You pick a choice, a C number for that one-dimensional space. Exactly. Yes, exactly. Yeah. This Frobenius algebra is also has a bijection with module categories, and the gap space is precisely labeled by the module category, and the vacua are objects in that module category, which is yeah. In the remaining time, let me describe an example of a rep S3 symmetric chain. And so I'm going to represent, I should say that what I'm going to describe was in a paper with Bottini, Leah Bottini, Sakura Schaefer Nameki, and Lakshay Bharadwaj. And there's also a complementary paper by Orko, who's in the audience, Omer Aksoy, and Xiaogang Wen. I think this is from May of 24. So I want to describe a rep S3 symmetric spin chain, and I again choose C to be vec S3. Okay, I should say that I represent S3 as following. It's generated by A and B. A is order 3, B is order 2, and BAB is 8 squared. So yeah. So again, we choose C to be vec S3, rho to be the direct sum of group elements, and we choose M to be vec. So it's the same model that described earlier. So the Hilbert space is a tensor product of G S3 qubits, and I want to in particular focus on two ground states, two gap phases and the transition between them. One is corresponds to choosing A labeled by Z3. Maybe A labeled by S3. And the other is A labeled by Z3. So this, the Hamiltonian for this is essentially going to disorder. So we have the algebra A is just a direct sum of group elements G in S3. Therefore, it's not going to project onto any subspace, but we're going to get a disordered sum of all configurations. So the Hamiltonian looks like minus summation. This is the projector one gets. RG is just RG is an operator that acts on the group element G, height I. Gives GI the right action on the state. And similarly, LG is the left action. And what one finds is there are three ground states. So firstly, one can notice that this Hamiltonian, it doesn't change so if you look at a spin chain with periodic boundary conditions and compute the product of group elements around the chain, it doesn't change the holonomy of that product up to a conjugation, perhaps. So what we get is, let me say three ground states, psi1, psi A, and psi B. That is a equal weight sum of all configurations with this product being in a certain conjugacy class, 1, A, and B. Sorry? So you can see that this Hamiltonian, what it does is it disorders configuration. So you can start with any configuration, you get another configuration. However, and it's also a projector, but it doesn't change the product of group elements around the chain up to it only changes it up to conjugation. It doesn't change the conjugacy class. And there are three conjugacy classes in S3, so you get three states. But these are in fact not the thermodynamic ground states. Those are some linear combinations of them. Have GS1, GSP, and GSE. The precise form of this linear combination is not important, but they're labeled by representations. And the symmetry action is just, I can take some symmetry operator labeled by some representation R, and it acts on the ground state labeled by R prime, and gives you, acts like the fusion of representation. So you get an R prime, or double prime. There's some three vacua state with ground states labeled by irreps. Now, meanwhile, there's another phase which is labeled by Z3 instead of S3. And the Hamiltonian kind of looks similar, but you also project. One needs to project onto, so for instance, this Hamiltonian requires that this vertical rung is projected to G in Z3. So, concretely, if one just works out the details, the Hamiltonian turns out to be -1/3 summation G in Z3. This R, G bar, LG. I'm not writing the indices as a shorthand, and -½ some projector. And the projector is also something like 1 plus ZP, J plus ½. This is a projector that can be constructed that just picks out the correct states. Yes, exactly. And I won't give you the details because they're not illustrated, but this Hamiltonian is easy to solve. One again gets 3 ground states, GSQ, Q equal to 0, 1, 2, and the symmetry action is like this. So it's invariant under, I should call this S, under the symmetry labeled by the irrep 1, irrep P. Meanwhile, E and this is mod 3. So what we find is that there are there seem to be two gap phases. Let me call it phase labeled by S3, so AS3, and another phase labeled by Z3. And they each have 3 vacua. Here 1, P, and E. And here they were called 0, 1, and 2. And one would never be able to distinguish these 2 phases by only looking at conventional symmetries because there's no obvious Z3 symmetry. So one would never find a 3 vacua state. And furthermore, we wouldn't expect a second order transition between 2, 3 vacua gap phases in such a system if we didn't know about the non-invertible symmetry. In fact, the transition also can be found exactly, and it turns out to be an Ising plus Ising transition. So what that means is that the state space at the transition decomposes into a direct sum of 2 state spaces, and the Hamiltonian, the low energy Hamiltonian in those decoupled state spaces realize the Ising Hamiltonian. But this is the dual Ising in the sense that they're related by some Kramer-Warnier duality. And let me describe how the S3 symmetry, sorry, the rep S3 symmetry is represented at the transition. Yes. Yeah. Yes. The first one corresponds to full gauging, yes. No, so there's some transition in the S3 symmetric model between 2 gap phases that you can just gauge the full S3 symmetry. So you'd start, I think this would be the paramagnet. Sorry, this would be the paramagnet, and this would be the Z3. This would be the Z3 symmetric phase. So I guess there's a gauging that takes this from, so this is the rep S3 symmetric phase diagram. And here we have, this is the S3 symmetric phase diagram. And this phase is the Z2 SSB. And this is the trivial phase, paramagnet, if you wish. And this is the Ising transition, which splits into a direct sum of Ising transitions as you gauge. So this way is gauging S3. Yeah. Which one? Yeah. Here this is, so yeah, great. So I would call this phase rep S3 SSB. Here I would call it rep S3 mod Z2 SSB. And why mod Z2? Because the Z2 symmetry acts trivially. Yeah. But let me tell you about the transition. The transition is quite interesting. I'm going to call this copy of Ising 0. I'll call this copy of Ising 1. The way the P operator acts on this transition is like the Z2 symmetry, or I'm calling it U in the one state space, plus the identity operator in the two state space. Meanwhile, the E symmetry acts like Kramer-Warnier, going from 1 to 2, plus Kramer-Warnier bar going from 2 to 1, plus U tilde, 1, 2, 2. U tilde being the dual Z2 symmetry of this U in the gauged copy of Ising. And one can show that SE times SE would be, for example, Kramer-Warnier 1, 2 times Kramer-Warnier 2, 1 plus these would be the terms that one would get. And this is just 1 plus U. This is 1 plus 1, 1, 2, 2 plus U tilde 2, 2. And here, this is like the P operator acting on Kramer-Warnier, so it should just be absorbed. So this is just Kramer-Warnier 2, 1. This is Kramer-Warnier 1, 2. And this is 1, 2, 2. You can see that this is just the identity operator. This is identity. This is SP, and this is SE. Yes, is a direct sum, yeah. Exactly. Exactly. Because the Hilbert space is block diagonal at the transition. You have like the Hilbert space decomposed into direct sum, and this is the matrix decomposition of that. So you see, like rep S3 is represented in a very non-trivial way at this transition. And really what is happening is, as you tune away from the perspective of this Ising plus Ising, this thing is like ferromagnet plus paramagnet, and this is paramagnet plus ferromagnet, both of which have 2 plus 1 and 1 plus 2, so 3 ground states, but they're kind of stabilized by this non-invertible symmetry. There's no reason for, I mean, as you tune away from the transition, both the copies have to be tuned together unless we break this non-invertible symmetry. I have like 1 minute remaining. I want to say that all of this can be kind of contextualized in the language of, in the framework of SIM-TFT, but since I don't have time to talk about it, I'll be happy to talk about it offline if someone's interested. Yeah, yeah. So that row has to be kind of rich enough to accommodate all the charges. So we know the representation theory of these symmetries. Those are labeled by, so that's actually related to the thing I was kind of mumbling about earlier, to the answer to the question that Abhishod asked. There's a SIM-TFT construction where you can take, you can define the spin chain on an interface between two boundaries, the symmetry and the physical boundary. And there are rows here, if you wish. Now, what we want is for every anyon in the bulk, that anyon projects onto some, so it has some projection on this boundary. It should not kill rho. It should be able to end on rho in a non-zero way. If it can do that, then it becomes a charge in the model. So to give you an example, let's take toric code again. And let's say I chose rho to be 1. Right? And this is the E condensed boundary. And this is also the E condensed boundary. Now, if I take the M line, what that M line does is it basically produces, it continues off in this boundary as a non-trivial defect. That non-trivial defect changes rho, so it kills the state space. In terms of the lattice model, what it means is that you don't have a disorder operator. So you can't tune into the paramagnet. The canonical answer, I mean, this is the only as much of a canonical answer I can give you, but I guess the answer is that your model should be rich enough to have the full spectrum of generalized charges. And the way one can check that is by looking at the projection of how these defects end on the input boundary, and whether they can end on rho specifically. I think in some case you might, maybe you need some multiplicity also. I'm not sure about that. Yeah. So I mean that, so in terms of this easing, plus, there's a U symmetry here, which is the Z2 symmetry, and there's a U tilde symmetry here, right? Now let me deform into the ferromagnet plus paramagnet on this side, right? So I get two ground states. One is a spin up, one is a spin down, and this is in the 0th copy. Oh, I'm sorry, I wrote 0 and 1 here, but I wrote 1 and 2 there. That must have been confusing. But so this is the 0th copy, and then there's a paramagnet. So there's some plus state in the 1 copy, right? So it's symmetry broken. So the U symmetry. So how does SP act? Recall that SP was like U plus 1, right? So it exchanges these two. So SP basically exchanges these two, and it acts invariantly on plus. Right? Meanwhile, SE was like Kramer-Warnier duals plus the U tilde, right? So SE would, for instance, it would take the state 1, so the state up to the state plus, because the Kramer-Warnier dual of this, it would take state down also to the state plus, but it would take plus to up plus down. That's what the Kramer-Warnier map does. But it also acts by U tilde, right? So you also get another plus here. But now if I read these as 1, P, and E, you see SE acts exactly like SE times E is 1 plus P plus E. And P sends 1, it exchanges 1 and P. So it's exactly acting like the fusion of representations. So you recover the rep S3 SSB phase. You can do the same thing on this side. It's a similar exercise.
More questions? If not, let's take Apoorv. We regather at 3 as usual.